Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Balasubramanian Sivan, aka Balu for short. Balu is a PhD student in University of Wisconsin-Madison, advised by Shuchi Chawla. And Balu has been an intern here. And during his internship, he worked on the so-called the water level algorithm, which has had a big impact. So over to Balu.
Thanks, Nikhil. Thanks for the invitation. I'm very happy to be back. So I'll be talking about optimization with uncertain inputs in this talk. And in particular, I'll be focusing on two kinds of uncertain inputs. One is as in online inputs, where the input comes piece by piece, and your algorithm has to make a decision as soon as one piece arrives and can't wait for the entire input. So optimization subject to uncertain future is the challenge here. And the second is as in mechanism design, where your input is distributed across several selfish participants, and each of them may have their own well-defined goals, which often conflict with the optimization goal of the algorithm designer. And the challenge is to do optimization respecting the incentives of these selfish agents. Okay. So I'll begin by asking, how do we formally model and analyze these problems in theory? There are several approaches to do this, but there are two main approaches which have gained currency in the CS literature. One is to do competitive analysis, where the algorithm you design faces the input uncertainty, but the benchmark against which you compare yourself is omniscient. It knows the entire input to begin with, and the performance metric is measured through what's called the competitive ratio, which is the worst case over all inputs of the performance of your algorithm to the performance of the benchmark. So as you can see there, the opt has a subscript I, which means it's an instance-wise optimal, but the algorithm is the same for every instance. So it's an explicitly more powerful benchmark than your algorithm. And for this reason, this being a robust benchmark, any positive result is great in a competitive analysis, and a good example of a positive result is the celebrated VCG mechanism to maximize social welfare. And for the same reason that it is a robust benchmark like this, it often leads to pessimistic results, and we'll see this in the talk in the two examples I'm going to talk about. Now, a frequent alternative, in particular to step around those pessimistic results in competitive analysis, is to perform stochastic analysis, where the idea is that the input is drawn from a known distribution. The algorithm knows the distribution and tries to optimize with respect to that distribution. The benchmark against which you compare is the expected optimal for the same distribution. And the performance metric is basically the ratio of the expected performance of the algorithm to the benchmark. As you can see there, both of them have a subscript f, which means the opt is not explicitly more powerful, and you can shoot for a one approximation. And because of this, there are several success stories in stochastic analysis. I'll just give one example. Meyerson's revenue optimal mechanism design is a great example of stochastic analysis. We know the distribution. But the biggest criticism for stochastic analysis is that you need to know the exact distribution in order to perform this optimization. And often you have noisy data about distributions, and that could render your algorithm really suboptimal if there is noise. So given these two extremes, a possible middle ground would be to say that the input may be drawn from some distribution, but I, as the algorithm designer, do not know the exact distribution. I only know the possibly huge universe of distribution from which the input arrives. And what I'm asking for is a single algorithm which, for every distribution in this universe, performs approximately as well as the optimal algorithm tailored specifically for the distribution. Okay. So basically, we are optimizing for the worst distribution in the whole universe. So even if you don't know the exact distribution, you can use the same algorithm for all the distributions. It is in this sense that the algorithms are prior robust, because you are blind to the exact prior distribution on inputs. As you can see there, the opt has a subscript f, which means it's distribution-wise optimal, tailored to the distribution. The algorithm is the same for all the distributions.
Does the algorithm see the whole input I at once, or?
I mean, it depends. So for online inputs, it's basically one by one. In mechanism design, you have to elicit the inputs. There, typically, you ask from all the people. Actually, for both the examples I'm going to give in this talk, we use an even stronger metric. The opt is not just distribution-wise optimal; it is instance-wise optimal. Okay. So it is even closer to competitive analysis. That way, just the presence of the distribution allows us to step around the negative results in competitive analysis. Now, this can be pushed to both extremes. If you shrink the universe to be of size 1, then there's exactly stochastic analysis. And if you allow the universe to include arbitrary distribution, every distribution possible, then that is competitive analysis. And the goal in prior robust optimization is to develop algorithms which can handle as rich universe as possible. Typically, these distributions, the universe has some structure. It is not an arbitrary bag of distributions. For example, all possible product distributions over inputs and things like that. Okay. So the question is, do we have any non-trivial algorithms with this model? And there are some nice examples. For example, the classic mechanism design result due to Bulow and Klemperer, and its generalization by Dangwort, Erafgarten, and Yan, and in purely algorithmic settings, the result due to Devnur and Hayes. I'll talk more about this later, but these are examples of prior robust optimization.
So when you talk about optimization, I'm not in this area, so pretty basic question. Are you talking about the errors of the computing results, or are you talking about the performance of the errors?
I'm talking about the performance of the algorithm. There is an objective function which you have, and I'm asking how close you can get to the objective function as compared to the optimal value of the objective function.
I'm in compiler, so performance to us is the computing speed.
No. Yeah. I mean, it's not a question of runtime here. We want it to be polynomial, but apart from that, the real performance is with respect to the objective function. You're optimizing. Okay. So that is the prior robust model. So the plan for this talk is to present prior robust algorithms for two fundamental CS problems, and the takeaway message is that several interesting problems lend themselves to this kind of prior robust algorithms, and you must look for them and develop them. So in part 1 of the talk, I'll present a prior robust algorithm for a resource allocation problem. And in part 2, I'll do mechanism design. I'll present a prior robust truthful machine scheduling mechanism. And I'll conclude with some future research directions. Okay. So part 1 is basically, it's based on a couple of joint works. One is with Nikhil Devnur, Kamal Jain, and Chris Wilkins. Other is with Nikhil Devnur and Yossi Azar. Okay. So this resource allocation framework, the formal framework, I'll present in a bit, but this framework actually is very general and captures a lot of problems motivated by internet advertising. So I'll quickly go through a couple of examples. So one is the display ads example. If you visit any website, popular website, you will see at least one advertisement like that. And at a very high level, you can think of this display ads as proceeding in 4 phases. Okay. In phase 1, the advertiser, which in this case University of Phoenix, signs a contract with the publisher like MSN, saying that I want so many impressions in this period to people between the age, so on, etc. Now MSN signs contracts like this with several advertisers, and then once contracts are signed, a user web page arrives, and MSN has to decide basically in the vacant spot which advertisement to put. Okay. Then you deliver these ads plus the content. So this third phase is basically a resource allocation phase. You have to decide which advertisement to put there in the vacant spot. And this next example is basically something you've all seen a ton of times. If you search for a query, apart from the organic results that you get, you also see some paid search results. And this can also be thought of at a very high level, proceeding in 4 phases, except that there is no contracts here. Okay. Advertisers submit bids and budgets, and when a user query arrives, the search engine has to decide which ad is to be matched. And basically, the phase 3 is the resource allocation phase. Okay. So I'll now go into the formal model of this phase 3. Okay. So the model I'm going to talk about is due to Mehta, Saberi, Vazirani, and Vazirani. It's basically an online model of repeated auctions. There is no incentives here. It's purely algorithmic. There's a bunch of advertisers. Each have specified some budgets. These budgets are the maximum amount you can extract from them over a day or some time period. And they've also specified bids on various queries, and as soon as a query arrives, the search engine has to decide whom to allocate it to. Once you allocate, you subtract the budget from that advertiser, and you keep on proceeding like this. Okay. So the formal model is that you have n advertisers. Advertiser I has budget bi, and queries arrive as follows. So there is this huge graph. The right hand side of the graph is all possible queries, and at every step you are drawing a query independently and identically according to an unknown distribution. Okay. So the universe of all distributions is basically universe of all possible IID distributions over the queries. Okay. I do not know the distribution. as the algorithm designer. I'm going to call Pj as the probability with which query j is going to be drawn. I do not know Pj. And Bij is the bid of advertiser I for query j. Okay. So your goal is basically to get an algorithm which maximizes the revenue, which is the sum total of all the allocated bits, respecting the budget constraints. Okay. So that's the model. Is the model clear? How the queries are drawn? Okay. So it turns out that all the results for this problem are parameterized by the significant parameter called the maximum bid to budget ratio. It's not difficult to see why this is the case, and I illustrate this through a simple example. You consider a regular matching problem. Regular matching means all the bids are 1, all the budgets are 1. So you have just 2 advertisers. And 3 queries, let's say that 2 queries are going to be drawn online. Let's say this is the probability distribution. Suppose query 1 arrives first, query 2 arrives first. Then irrespective of what you do, there is a constant probability that the second query can't be allotted to anybody, right? You can, this guy's budget is over, and you can basically get a gap between optimal online and offline revenue. The point is that if instead of the bids being 1, suppose they were 1 by 1000, then each mistake you make is not going to be as costly as the bids being 1. Right? The bids being 1 is a big mistake. If it's 1 by 1000, it's lesser mistake. So obviously, if you have smaller and smaller bid to budget ratio, you can get better and better approximations. So all the approximation ratio have to be parameterized through this bid to budget ratio, and I'm going to call this gamma hereafter. Okay. So I'll present what is known now. So MSVV, who coined this problem, studied this problem in a competitive setting, and what they show is that you can get a 1 minus 1 by e approximation in the case when the bid to budget ratio is 0. Right. So this is the best case you can ask for when the bids are infinitesimally small compared to budgets. And even then you can get only 1 minus 1 by e. No randomized algorithm can go beyond 1 minus 1 by e. Okay. So that is for the competitive setting. And in a recent result, concurrently with our work, Saeed Alay, Mohammad Taghi, Haji Agai, and Mahat Liagat show that in a stochastic setting, okay, which means you know the distribution, you can get a 1 minus square root gamma approximation, where gamma is the bid to budget ratio. Okay. What this means is if gamma goes to 0, then you can get arbitrarily close to 1, circumventing the bound here that you cannot go beyond 1 minus 1 by e. Okay. The question we ask in this work is, can you get the same 1 minus square root gamma approximation but through a prior robust algorithm, which means you use the same algorithm irrespective of what the distribution is. Okay. So here's our results. It's the same model, IID model. We don't ask for the full distribution, but we ask for n parameters from the distribution. Okay. I'll explain what these n parameters are later, but the whole distribution itself could have an infinite support, but we only ask for a few parameters from the distribution, and given that, we get the same 1 minus square root gamma approximation, and we also show that you cannot go beyond 1 minus square root gamma even if you knew the distributions. Okay.
Does n appear somewhere else?
N doesn't appear in the approximations at all.
Whatever n is.
Oh, the n is the number of advertisers. Yeah, yes. So yeah, n is the number of advertisers, m is the number of queries, but the approximation ratio is independent of n. Yeah. Okay. So that's the result. So this same problem has been studied in a prior robust model with a slightly different universe than the IID universe of distributions. And in order to put our results in context, I'll briefly go through that model also before giving the proof of this result. Okay. So the model is the same as this model, except that instead of queries being drawn IID, an adversary initially picks the set of m queries to arrive. After that, these queries are sent according to a uniformly random permutation. Okay. So in IID, if you condition on the set of queries to arrive, they arrive in a uniformly random order, correct? So you can think of the IID model as a distribution or random permutation models, because in the IID nobody is conditioning on which queries to arrive. So IID is a distribution of random permutations, and for that reason any approximation ratio that holds for this random permutation model also holds for the IID model, but the reverse is not known and there is no separation results known for this. But the distributions are unknown, so basically the unknown IID model is really close to the random permutation model, though one of them is stronger than the other. Okay.
It's like sampling with and without replacement.
Yes.
So the queries must be distinct, or it's with repetitions?
It could be possible with repetitions. So here is what I already showed. So in the for the random permutation universe, actually the first result which showed that you could get arbitrarily close to 1 was the result by Devnur and Hayes, and this is the dependence on n and m they show, and there after this result there are several other results with different trade-offs. Basically the point is that all these depend on n and other parameters, but for the IID model we completely get rid of n and get this 1 minus square root gamma approximation, and it is an open question actually whether our algorithms actually extend to the random permutations also. Okay. The first question is whether random permutations actually permit this kind of approximation without any dependence on n, but then you could ask whether this algorithm itself actually extends to random permutations.
So there are no any lower bounds for the random permutation model?
There is no known lower bound except for this itself, which is for IID. Okay, so that's the comparison for between IID and random permutations. So I'll now prove this result, this 1 minus square root gamma. Here are some simplifying assumptions just for the purposes of the stock. First, I'll assume that the bids are binary, okay, 0 or 1. The second is that the distribution is a uniform distribution, all queries, that every query arrives at the same probability of 1 by m. M is the total number of queries. And for the third assumption, I'll need a quick definition. Okay, I'm going to define what is an expected instance. For every distribution, this is a single offline instance where everything happens as per expectation. Okay, so you have query j which arrives with probability pj in the online model, which means the expected number of times it should arrive is m times pj, right? So in the offline instance, this expected instance, you have exactly m pj units of query j. Okay, so for every query you have an expected number of units of that query in this offline instance. In particular for this example, m times pj is exactly 1, so you have 1 unit of every query in the support of the distribution, and that is a single offline instance, and you can't compute it if you do not know the distribution, right? If you know the distribution, this is offline instance, and the assumption is that you have a perfect matching in the expected instance. The optimal solution to the expected instance is perfect B matching, which means that every advertiser's budget is fully consumed. Okay, I'll examine all these assumptions later, but for now let's say that every advertiser's full budget is consumed. Okay, so given these assumptions, what can you do? Okay, if you knew the distribution, then you can run this algorithm. That's why I'm calling this a hypothetical algorithm, because you do not know the distribution. So here's what the algorithm does. It firstly computes the expected instance for which you need the distribution, right? You need to know the number of queries which arrive, and it finds the optimal matching for the expected instance. Okay, so that is, you find the matching and tabulate it as a table, which query goes to which advertiser. It stores this table, and it uses the solution for the online problem. Okay, so what does it mean? Let's say a sequence of queries arrives like this. When 3 arrives, it goes to the table and sees it should be given to advertiser 7. You give it there. When 1 arrives, you do the same thing, go to the table and see. When 3 arrives again, it says advertiser 7, it will give it to advertiser 7, even if by this time advertiser 7's budget was exhausted. It could be that 7's budget is exhausted, but that is why it is an oblivious algorithm. It doesn't depend on what has happened earlier. It is a waste of money to give it to 7, but I will still give it to 7. Okay, it's a simple non-adaptive algorithm.
So what does it mean? So it won't be a feasible solution, or?
I mean, there is nothing like feasible. I mean, you can keep on giving it to the advertiser, but he won't pay beyond BI. I mean, you won't get the money. It's a waste after BI, that's all.
Only theorists would consider that feasible.
It's also hypothetical.
Yeah, that's why it's hypothetical. Yeah.
Oblivious to the fact that it's impossible.
The claim is this simple non-adaptive algorithm actually gets 1 minus square root gamma approximation, and for the assumptions I made, gamma is just, gamma is bid by budget and the bids are all 1, so it is 1 by the minimum budget, right? So I am shooting for a 1 by square root 1 by budget approximation, 1 minus square root 1 by budget. Okay, so here is the proof for this. Let's analyze this step by step. In any given step, let's see what happens. What is the probability that advertiser I gets a query? Well, I said in the expected instance, you have full budget consumption, which means advertiser I had BI queries going to him. Okay, so if any of those BI queries arrived, then advertiser I would have been given that query. Okay, there is a total of m queries. So the probability that advertiser I gets a query is BI by m in any given step. Okay, so now this algorithm is basically like a balls and bins process. At every step, it is throwing a ball to advertiser I with probability BI by m, And what is the revenue at the end of all the steps? Because I've assumed binary queries, the revenue is basically the number of queries which is matched but truncated at bi. Like you asked, there is no use of giving beyond bi. And this is basically then a truncated binomial sum. We know that a truncated binomial sum has a square root loss, and you basically get the result. You sum over all these people, and that's the total revenue. So if you know the distribution, you can run this simple algorithm. I want to point out two things about this algorithm. One is the computational burden of this algorithm increases with the size of the support, which means to compute the expected instance, you need to know the full support and compute the expected instance. So the support grows larger and larger, the computational burden of this grows larger, and if it is infinite, this is rendered infeasible. Secondly, this is also this could be a randomized algorithm, because the table you get, for the example I had, it's a proper integral table, but it could be fractional.
Yeah, so this ratio you're computing is the ratio of what the algorithm achieves to what exactly?
What the algorithm achieves to what you can achieve through in an offline fractional solution, optimal offline fractional solution. So as you
and that's essentially the same as this thing that you computed in advance.
Yes.
With the expectation, I think.
Exactly. Yeah.
It's an upper bound of the expectation of the optimum.
So it is basically the opt for the expected instance, which is larger than the expectation of opt.
Okay.
Because the expectation of opt will be a feasible solution here, so the opt of the expected instance will only be larger. Okay. So that is why I said in the benchmark slide, it's a stronger metric, which is an instance-wise optimal. That's why I'm looking at offline optimal solutions. Okay, so this is what you do if you know the distribution, but you do not know the distribution. What do you do? So consider running the following hybrid algorithm, which is a hybrid of the following two algorithms. One is the hypothetical algorithm we just presented. Other is an algorithm A, which is going to be inductively defined now. And HI is a hybrid of P and A, which runs P for the first I steps and A for the remaining A for the first I steps and P for the remaining I steps. It's A followed by P. Okay. So let's assume that A has been defined for the first I steps, and I'm going to define what it does at the I plus 1th step. Once a query arrives, it picks the following advertiser. The advertiser which maximizes the current step's revenue plus the expected residual revenue which you achieve if you run the hypothetical algorithm for the remaining m minus I minus 1 steps. So you look ahead and decide the best thing to do now. Now by definition, the hybrid HI plus 1 will get a higher revenue than the hybrid HI, because HI plus 1 and HI differ only at the I plus 1th step, and the HI plus 1 basically runs this algorithm A, which looks ahead and makes the decision, whereas HI does this the hypothetical algorithm, which actually looks at the table and does something. And clearly this opt to looking ahead and doing something is better than looking at the table and doing something.
So the hypothetical algorithm learns, this is, you still assume that you know the distribution or you no longer know?
I mean, I want to show that you can do this without knowing the distribution. But for now, suppose you could do this. Suppose you could look ahead and make this decision. Then I'm saying HI plus 1 is better than HI. Just the I plus 1th step is different, but by definition it is better. Now you can slowly change this step by step, just like you prove indistinguishability in cryptography. And at the end, basically the point is if you run the algorithm A all the way, it is better than running algorithm P all the way by definition. And I already showed that P gets this square root loss, which is what we wanted, which means A also gets it. The question is, can you run this algorithm A? Because I said you have to look ahead into the future and decide this expected, compute this expected revenue. So the key idea is that implementing this hypothetical algorithm actually requires knowledge of the distribution, but just estimating its revenue doesn't require knowledge of the distribution. Okay, and all we need is to estimate the revenue. Why is that? Because I said this hypothetical algorithm is a simple balls and bins process, which throws a query into advertiser I with probability bi by m. I know the budgets bi. I know the number of queries m. So at any given point in time, given the number of remaining queries, I can estimate the residual revenue with the number of queries remaining and these numbers. It's a sum of binomial expressions, one for each I. So I can estimate this exactly, and the upshot is that you can run the hybrid algorithm without knowledge of the distribution. Okay, all I ask for is these numbers. Now one point is that it is not enough to recognize that this P can be interpreted as a balls and bins process with probability bi by m, even after knowing that you cannot implement P itself, okay, because you're not given a bunch of balls and asked to play a balls and bins process here. As a query arrives, you have to decide whom to assign it to. So you can't run this algorithm P, but because you can estimate the revenue of P, you can run some other algorithm which does as well as P. Okay. So that's the point. So I will wrap up this analysis by examining some assumptions I made. One is, I said it's a uniform distribution. What if it is not? And this turns out to be not a major assumption. The expected instance will now have a fractional optimal solution instead of this integral optimal solution. That is fine. It only changes what the hypothetical algorithm does. It will be a randomized algorithm, but it doesn't change anything about how the algorithm A itself is defined inductively. It's
the complexity of all these algorithms doesn't depend on the hardness of the distribution, right? I mean, if the distribution was very easy, say, had very low entropy, you could presumably think that you can invest the first squares to learn it and then do whatever.
Yes, so yeah, the algorithm I presented doesn't depend on, the complexity doesn't depend on.
You could imagine that for several distributions you can do better than the square root?
No, even if you know the distribution, you can't. Even if you know the distribution, you can't go beyond the square root class because I'm comparing it with the offline optimal solution. It's not the online optimal.
I guess what I'm asking is whether for the offline solution, is it conceivable that offline solution can do better than the square root for some distributions?
What does it mean to say offline will do better than square root?
You have, suppose you know the distribution.
Yes.
Right?
Yes.
So is the square root, the 1 minus square root?
Oh yeah, I mean it doesn't hold for every distribution. Yes. I mean.
So you could imagine.
You could, yeah. I mean it's only that there are distributions for which you can't go beyond 1 minus square. Yeah. Okay, and the second assumption I made is that the bids are binary. This is a more serious assumption. What happens if they are not binary? Well, there could be anywhere between 0 and 1. Now you can't interpret this hypothetical algorithm as a balls and bins process anymore because you're throwing balls of different sizes, so it's like a fractional balls and bins process. And this complicates the hybrid argument, and you basically have to introduce a third algorithm F and do a 2-level hybrid argument to give this proof. I'm not going to go through that, but you can get the same approximations for arbitrary bits without any relaxations. The third assumption is that I said the budgets are fully consumed in the expected instance. What if you don't get full budget consumption? You consume something which is lesser than bi. The only difference is then the balls and bins probability now is ci by m instead of bi by m. Okay, you do not know these ci's, and this is what our algorithm asks for. These are the n parameters. Okay, if you give me the consumption, optimal consumption in the expected instance for every advertiser, if you give me these ci's, then I can use them to estimate the residual revenue and run the hybrid algorithm. Okay, so those are the n parameters we need. If you give me them, I'll give what I promised. But here is an interesting open question which is immediate from this. What if you simply assume, make a wrong assumption? Just say that Ci is equal to Bi, right? And then run our algorithm. Does it perform well? We are able to prove that for some special cases this already does well. And if you're able to prove that for all cases it does well, then you're basically completely eliminated all dependence on the distribution. You're doing as well as the known distribution case. I think that would be great to prove that.
So, other question. In practice you wouldn't expect to actually know these CIs, right? But maybe you could estimate them.
Sure, yeah, you can only estimate a stand-in for these CIs. Yeah, I mean,
and you can prove something that if you know the CIs within epsilon, then.
Yes. If you can know the CIs within epsilon, these results also will be within epsilon. Yes. Okay, so that is the immediate open question from this. Now I'm going to generalize this to a much more general resource allocation framework, which I said I'll present later. And this basically captures all the special cases I said, and then online combinatorial auctions, online network routing, and so on. So the model is that you have m requests, like the m queries. You have n resources, like the n advertisers. Resource I has budget bi. The major difference is that now every request, instead of just consuming resource from one resource, can simultaneously consume resources from all the resources available. Okay, so I'm going to introduce a third number, which is an option to serve a given request, And if you serve request j with option k, you get a profit of wjk, and it consumes some amount of resource from every advertiser. It consumes bijk from advertiser I, or the resource I. To have a concrete example in mind, think of the requests as, think of you having a graph and the requests as requests to route from some source and sink in the graph. The resources are the edge capacities in the graph, and the option is basically which path you have to choose from the source to the sink. So you have an exponential number of paths to choose. So the number of options is exponential in n, and obviously different paths consume from different edges. So that is the consumption information. So in general you have bijk amount of consumption from resource I. Okay. So this is the general resource allocation framework. And here's our results. Again, the inputs are drawn IID. We do not know the distribution. In this case it's completely unknown distributions. We don't even ask for any n parameters. In other words, you can use this algorithm for the previous results I said, the previous problem I said. Only thing is the results are slightly worse here. You have to depend on n here, unlike the 1 minus square root gamma I presented earlier. The optimal depends on n, and we also show a lower bound matching, which says that you cannot get beyond 1 minus square root gamma log n for this general framework. This is with complete unknown distribution, and also these results hold with high probability, not just an expectation, they hold with the probability of 1 minus square root gamma log n. Okay. The high level idea is to use hybrid argument again, but the algorithm is fundamentally different. We use hybrid argument not on the expected revenue they presented, but hybrid argument on the exponential moment generating functions used in Chernoff bounds. To compare it with what's known, the previous best was 1 minus square root gamma n log kn, and as I said, k is typically exponential in n, like in the paths example, there are exponential number of paths. So if you have 2 to the n here, if you bring an n here, it's really square root of n square, or an n sitting here in front of the O, and the n is gone in our result basically. So n is typically large in these examples. But this is for random permutations, which as I explained is slightly stronger than the unknown IID model. So an immediate question here is, does our algorithm extend to the random permutation model with the same approximation factor? So that's the summary of part 1. For the special case of Adwords, we get matching upper and lower bounds, but we ask for n parameters of the distribution, and for the more general resource allocation framework, we again get matching upper and lower bounds, but this is with completely unknown distributions. So this work was done while I was an intern in 2010 with Nikhil, and thanks to Nikhil we were able to speak to the product groups, and they basically use this algorithm now for MSN's display ad serving engine, okay, for pretty much the exact problem I said, display ads problem, and it has been globally operational since the summer of 2011. Okay. So these are the open questions which I already presented, but I will repeat them. One is to see whether the IID and random permutation model have any separation. No separation is known. My own guess is that our algorithms actually work for random permutations, but we don't know. Other is to remove the dependence on the n parameters, these CIs. Okay. So that's it for part 1. If you have questions, you can ask questions about part 1. I'll now be moving to mechanism design. Okay. So I'll now talk about a prior robust truthful machine scheduling mechanism. This is joint work with Shuchi Chawla, Jason Hartline, and David Malik. So the problem is the very well studied makespan minimization problem in computer science. You have n jobs and m machines, and jobs are different runtimes on different machines, and your goal is to find a schedule of jobs on machines to minimize the completion time of the last job. Okay. So if you have this jobs and machines, machine 2 is basically the makespan defining machine for this schedule. Okay, and this is called an unrelated instance because for any given job the runtimes on different machines are completely unrelated. Okay, so this is the problem we study with the twist that we're going to study this in a strategic setting. Okay, this problem was introduced in the seminal paper for algorithmic mechanism design by Nissan and Ronen, where they say that these machines are operated by selfish workers, and the runtimes of jobs on machines are privately held by machines, and you do not know these runtimes to begin with. And what we ask for is a mechanism which is not just a schedule of jobs on machines, but along with that some payments which you transfer to these machines to incentivize them to truthfully report their runtimes. Okay, this pair of schedule plus payments is the mechanism, and the machines have their own selfish objective, which is to maximize the payment they receive from you minus the work they are forced to do, which is the sum total of the runtimes of all the jobs they are asked to run. Okay. And the solution concept I ask for is dominant strategy truthfulness, which means a mechanism which, irrespective of how other machines behave, will make each machine is incentivized to report its true runtimes. Okay. This is the strongest notion of truthfulness one could ask for in mechanisms. Okay. So what's the motivation to study makespan in a strategic setting? There are several. One is that it's a central computer science problem, specifically in the context of resource allocation. Even from an economic point of view, makespan is, you could think of makespan as enforcing some kind of fairness. After all, makespan is load balancing between machines, so it's like a min-max fairness. What makes it really interesting to me is that it is a non-linear objective, unlike other traditionally studied objectives in mechanism design like revenue and welfare, which are all linear, and for this reason what is possible for makespan is very different from what is possible for makespan is very different from what is possible for welfare or revenue. And here are some differences. For example, the social welfare objective, which is the most well studied objective in mechanism design, you can get truthfulness plus optimality through the celebrated VCG mechanism. Okay. If you didn't care about computational considerations for a minute, then you can get a truthful mechanism which optimizes social welfare all the time. Okay. But truthfulness plus optimality itself is impossible in makespan, as Nissan and Ronan showed in their original paper. This means that even if I give you unbounded computational time, you cannot give me a truthful scheduling mechanism which will optimize the makespan. Okay. There are some hardness results there, and I will trace through the entire hardness results in the next slide. Another striking difference is that the kind of impressive reductions that was possible in social welfare, where you take an arbitrary approximation algorithm and you inject truthfulness into it. You can morph an algorithm into a truthful mechanism, and it will preserve the approximation guarantee of the original approximation algorithm. Such kind of impressive general reductions are not possible even in the simplest of settings in makespan. Okay, this again is a big difference. And this problem was basically introduced as a challenge problem for mechanism design by Nissan and Ronan in their seminal paper, and since then this has become a hot area to work on, and let's see what is known. So Nissan and Ronan give a simple M approximation in their original paper, but much activity has been on lower bounds for this problem. So the authors in their original paper show that no deterministic mechanism can get anything beyond a 2 approximation. Okay, even if you give unbounded computational time, there is no computational restrictions here. And this was later improved to randomized mechanisms also by Moelem and Shapira, and then this bound was improved several times later by Christodoulou, Koutsoupias and Vidali, later by Koutsoupias and Vidali, until recently where Ashlagi, Dobzhinsky and Lavie showed that the upper and lower bounds match basically. Okay, there's a very big hardness result here, although the hardness result holds for only a restricted class of mechanisms called anonymous mechanisms. Anonymous mechanisms means that you should not use the name of the machine to make your decision, which means if two machines swap their runtimes, then how you treat those two machines also should be swapped. Okay, so given this backdrop of hardness results, we ask in this work, if you make stochastic assumptions, can you get a prior robust truthful mechanism which gets good approximation for makespan given all these hardness results in the competitive setting? Okay. That's the question in this work. Okay, so I'll now formally present what is a distributional model for scheduling. Okay, so we have n jobs and m machines, and the runtime of job j on machine I is xji, and these xji's are independent random variables. And here's what I assume about the distribution: the runtime distributions are identical across machines. Okay, for a given job, the runtimes of the job on the different machines are IID random variables, but the jobs themselves could be non-identical. Okay, so you see there. So basically the machines are a priori identical. Okay, but if you draw the runtimes from these distributions, any specific instantiation of these runtimes will lead you to an unrelated instance. Okay, so I'm going to use a short form for machines being IID and jobs being non-IID, but this is what I mean. For some results, I also need that the jobs are also IID, but I'll present them when I present the results. The goal is to minimize the expected makespan, like before. Okay.
Do you know the distributions in advance?
And no, I want to get a prior robust mechanism, which means for all possible distributions which just satisfy these conditions, independence and IID. So this is what I showed you already, that the upper and lower bounds match in the competitive setting for a restricted class for the lower bound though. And the stochastic setting is completely open, which means if I give you the distribution, can you do something better? That's not known. Here's our results. We give a prior robust truthful mechanism which gets an order of n by m approximation for opt half. N is the number of jobs and m is the number of machines, m for machines. In particular, when n is equal to m, this is like a constant factor approximation, and this lower bound there also holds for n is equal to m. So basically you can get a constant factor for those. The benchmark for us is opt half, which is basically the non-truthful, it's allowed to, opt is allowed to be non-truthful. So it's the non-truthful expected optimal, but it is allowed to use at most half the machines. So it's like a resource augmentation result. Okay. So I'll explain this benchmark opt half in a bit, but this is our first result. And later we show that you can improve this to sub-logarithmic factors if you assume that the jobs are also IIT and make further distributional assumptions. Okay. So those are our results. I'll now go through this opt half benchmark and explain it a bit. As I said, opt half means that opt is allowed to use at most half the number of machines which you are allowed to use. So if you get good approximation to opt half, it means that you can do well with resource augmentation. Okay. If you double the number of machines, you can perform approximately as well as opt. In general, this opt half could be much larger than opt, but we show that for a large family of distributions, opt half and opt are within constant factors, which means that it's really not a resource augmentation result for these distributions, okay, because it's only a constant factor away. For monotone hazard rate distributions, intuitively these are distributions which have tails no heavier than exponential distributions, which includes uniform, normal and exponential. This is basically true, and even for a larger class of distributions, much larger class, opt half and opt are within constant factors. Okay, I won't talk about the class now. So that is about the benchmark opt half. So I will now sketch the proof of how we get this order of n by m approximation. Particularly, I'm going to assume that n is equal to m, and I'm going to shoot for a constant factor approximation in the proof. Okay, I'll sketch the proof. To get a flavor of what is truthful, what is possible in this multi-parameter setting, let's begin with a very simple mechanism which is truthful, and this was introduced by Nissan and Ronan. This mechanism is called the min work mechanism. Okay. It just minimizes the total work done by all the machines, which means it tries to minimize the sum total of the runtimes of all the machines. Okay. This has nothing to do with makespan. So whenever it takes a job and basically schedules the job on the machine which has reported the smallest runtime for that job. Okay. That's what it means to minimize the sum total of all the runtimes. And it pays the machine the job's runtime on the second quickest machine. Okay. So this will result in a truthful mechanism. You should just take my word for it, I won't prove it.
This is just like the second price option,
yes,
independently for each
exactly
job.
Yes, and that also minimizes the total global runtime also. Right.
It's just independent for each.
No, it is independent for each job, but that's exactly what you will do if you want to minimize the total runtime. You need not do anything global actually. You can do locally to minimize the total runtime.
But if you minimize the sum, can't you apply VCG?
This is exactly VCG basically. It's VCG for, we are doing a reverse auction. It's a procurement auction here. So instead of maximizing welfare, you are minimizing the burden basically. So you're minimizing the total runtime.
One more question. So the revelation principle doesn't apply to certain objective functions. That's why you can't apply it in this setup?
No, the revelation principle applies, but that just says that whatever you can do with a non-truthful mechanism, you can also do with a truthful mechanism. But this objective is a different objective, right? You are minimizing the total work. My goal is to minimize makespan. I'm simply giving a mechanism which is just truthful, and it has some non-trivial approximation for makespan. That's all. You can use this mechanism for makespan, but it will be bad. That's what I'm going to talk about now. So this simple mechanism already gives a M approximation where M is the number of machines. This is a simple thing because the makespan is just a max. Max is always lesser than the sum. The sum of the quickest runtimes is always less than sum of the runtimes of all jobs in opt, which is at most M times the makespan of opt. Okay. This was the Nissan-Ronan thing. You can get M approximation. And it's also truthful. So what else is truthful? Just to get a sense of what is truthful. It turns out that if you minimize the total work over a restricted domain of schedules, that is also truthful. Okay. You put a pre-specified restriction on what kind of schedules are possible before you ask for the runtimes. Then try to minimize the total work over this restricted domain of schedules, and that is also truthful. So the natural question is, why can't you try this simple mechanism first? Maybe it does better in a stochastic setting because that was for a worst case setting that I gave an M I showed an M approximation of Nissan and Ronan. So let's consider the simple example. You have M jobs, M machines. Everything is IID. Okay. All jobs and machines runtimes are uniformly drawn between 1 and 1 plus epsilon. Now, the quickest machine for a job is a uniformly random machine, right? Which means that the min work mechanism, when it assigns a job to quickest machine, it's basically assigning a job to a random machine. Okay. So you're basically throwing balls randomly into bins, and a fundamental fact from the balls and bins analysis is that the heaviest loaded bin has log m by log m balls. Implications in logarithmic approximation is trivial, but we are looking for much better approximations like constant factor or at least sub-logarithmic approximation. Okay. So what is the problem with this min work mechanism? It is basically overcrowding machines, like what is happening there. It gives too much importance to putting a job on the best machine, quickest machine possible. So a natural next step would be to explicitly prevent this overcrowding. So what if you say that you should not schedule more than k jobs in any machine? Okay. So that is a restricted domain of schedules. You run the same min work mechanism. You try to minimize the total work over this restricted domain of schedules of at most k jobs per machine. That's what I call the min work k mechanism. Minimize the total work with at most k jobs per machine. This is truthful because it's a restricted domain of schedules, and it's also polynomial time because it's a minimum size matching problem. Okay, each machine has a degree of k. The claim is that this min work k mechanism gives a constant factor approximation for opt half. The proof idea is basically roughly these two steps. First is that min work k mechanism results in a roughly balanced schedule, unlike what could be the lopsided schedules that occur in the min work mechanism. Secondly, in spite of the fact that I put a restriction on the number of jobs which go to a machine, it is not necessary that hereafter a job goes to its quickest machine. Still, it basically a job roughly goes to its quickest machine. What is k here? K is the number I'm going to put, the restriction I'm going to put that at most k jobs can go to any particular machine. Okay. You cannot crowd beyond that. You're optimizing. I'll choose k. I'll make k 10 basically. Yeah. I mean k is a constant and I can choose k to get a constant factor approximation. Our results use k equals 10.
So you assume that m is equal to n?
Yes, okay, so m is equal to n, but if you have more jobs than machines, then 10 times n by m number of jobs, that's the restriction I put. So it's the average basically, 10 n by m. So here it's 10, and that's why the order of n by m factor comes out basically. Okay, so the second point is that though a job necessarily, not necessarily goes to its quickest machine, it roughly goes to its quickest machine. So here's the proof sketch. I'll just present the two key lemmas. The first lemma is that the probability that a job goes to its ith favorite machine, if it ranks the machines according to runtimes, is basically exponentially decaying in the rank of the machine. So it doesn't go too below in its preference order. The second lemma basically nicely complements the first lemma, that placing a job on its ith quickest machine is no worse than basically phi to the I, basically placing phi to the I independent copies of a job on their quickest machines. Okay. So opt, basically the only thing you can assume about opt is that it always puts the jobs on the quickest machine. So that's the best thing that is possible for opt, but it's the quickest among m by 2 machines. Okay. So this ith order statistics phrased purely as a probabilistic result, this says that the ith order statistic is almost stochastically dominated by an exponential number of phi to the I independent copies of first order statistics. The ith order statistic is among m independent draws, but the first order statistic is handicapped with m by 2 independent draws. Okay. So that is the purely probabilistic version of what we are showing. And these two basically you can see that these two coupled together to give a constant approximation because the I is the rank to which a job goes is exponentially decaying in I, and this is we have an exponential number here. So I'll just summarize part 2. When the machines are IID, when the jobs are non-IID, we give a prior robust mechanism which being blind to distributions, it can give a constant factor approximation when n is equal to m or order of n by m approximation. And as I said, opt half and opt are comparable to a large class of distributions. So it's not resource augmentation for those distributions at least. And when the jobs are also IID, you can further improve this to sub-logarithmic approximations, again with the prior robust mechanism. So I'll wrap up with open questions. One obvious open question is how broad a class of distributions can you tackle with prior robust mechanisms? Okay. In particular, can you relax this jobs being IID here, and can you have non-IID and still give this sub-logarithmic approximations? Other question is, I mean, this is much beyond the scope of this work at least. If you relax the IID assumption on machines, okay, everything I said breaks down there, and you need completely fresh ideas. The second open question is, can you improve what is possible for the competitive setting? Where as I said, the upper and the lower bounds match, at least for this anonymous mechanisms. Can you slightly relax the model and get positive results? Okay, here is one relaxation possible. Computer jobs, computer programs need not necessarily run on one machine. You can run the same program on multiple machines, and you can take the completion time to be when the first copy of every job completes. Okay, it's not a physical constraint. This will help in in-situ compatibility. You can ask what's the use of scheduling a job on multiple machines, but this will help in in-situ compatibility. For example, you could schedule all jobs on all machines. That's a possible schedule. And that is truthful. Only thing is it does too much work. If you also put a restriction on the maximum amount of work that can be done and allow a job to be scheduled on multiple machines, can you do something better?
You have to pay each machine that is scheduled.
Yes. So but it could be possible that you want to put a restriction on the total work to be done. Right? If you simply schedule all jobs on all machines, then that is possible to get the best makespan possible by just adjusting the order. That is truthful. No incentives for any machine because you don't use the runtime of machines at all. But every machine does too much work. So you put a restriction on the maximum work that can be done. And that is one way to circumvent the lower bounds in competitive setting. So I'll just briefly mention a selection of other results that I've done before mentioning future research directions. One problem that I've recently worked on is the design of optimal crowdsourcing contests. In a crowdsourcing contest, basically a principal or a firm has a task to be completed, and it advertises this task to a crowd, and it puts a reward, and these users or the crowd basically have submissions for this task, and you evaluate the task according to some pre-specified criterion and split the rewards among the winner or some winners. So the obvious question which arises is, what format of a contest should you use to incentivize users to give good submissions? In particular, the question we ask in this work is, how do you optimize the quality of the best submission you receive? Okay. A good example to have in mind is the contest which many of you may know that Netflix ran recently. Netflix ran a contest to improve the prediction accuracy of their algorithm. They wanted to basically predict how much a given user will like a particular movie based on how much he liked a given set of previous movies. And they promised that any user who improved the prediction accuracy of their algorithm, first user to improve the prediction accuracy of their algorithm by 10% will get $1 million. This contest is over now. So that is one model. So what is the best contest format? So for the model we use, we say that our result is basically that there is a very simple contest format which optimizes the quality of the best submission, which is basically you get all these submissions and segregate these submissions into different buckets. Okay. To go back to the Netflix example, you segregate all improvements between 10 and 12% in one bucket, 12 and 14% in one bucket, and all those users who fall in the biggest bucket will basically share the reward equally. And that is the optimal format. That's what we prove.
Why is it better to just give the whole amount to the winner?
Okay, so there are two things. One is, what is the best thing to do if you run a static contest? Static contest means you should not you should not decide how much amount you're giving to which person after you have received the submissions. This is what Topcoder does, for example. It runs these architecture competitions where it says 2/3 of the award will go to the best submission, 1/3 of the award will go to the second best submission. Among all those static contests, we prove that it is best to give everything to the winner. Winner take all is the best. But obviously a dynamic contest where you are allowed to see the submissions and then decide what to do later will do better, right? For example, when I say 10 and 12%, 12 and 14 are different buckets, the number of users who fall within 12 and 14 will basically vary based on the submissions. And after that, if I do something, the dynamic is always better than static.
But the question is, you're saying this is better than giving everything to the just the highest one.
Yes.
Right. So why is that? Is there any
Well, I mean, the buckets we decide are basically based on the distribution. And for some distributions, it will turn out that the buckets are all independent. There's no bucket at all, which means that everything will go to the winner. That is also possible. For many so-called regular distributions, it might turn out that there is no bucketing. But if the distribution doesn't, there is some monotonicity involved in the allocation function, and we do what is called the ironing of the allocation function. That results in bucketing. But suffice it to say that it could happen often that you will give everything to the highest bidder, highest quality.
Round. So you seem to be claiming there are some situations where you don't want to do that, and that's what we're more interested in. Can you explain?
it depends on the distribution. So
Right.
an example of the distribution.
It depends on the distribution, basically, why that arises.
Example.
What is the distribution over it? What's
So the agents have skills, basically. So you can think of skill as the rate at which an agent can do useful work. The quality of the submission is the product of the skill and the effort of the agent. Okay, so it's a linear model. So skill V times E, effort is P, which is the quality of the submission. And you have distribution over these skills. Okay. So you can map it to auction theory. We basically extend auction theory to model this. Now the only thing is in auction theory, for revenue you study the sum of the payments, here you study the maximum payment. Okay. So you could implement the same thing instead of dividing all this revenue in the highest bucket equally. You can also break ties, but you should break ties basically in a consistent manner. Instead of dividing things equally, you can always say that if all these people fall in this bucket, I will always give everything to advertiser 1 if he falls in this bucket, and then to advertiser 2. So there is a way to run these things without splitting rewards equally also, which works.
If the distribution is sort of continuous and there is unique optimal submission because of that, is it always true that we need to give it to the person who submitted the best solution, or it's also not necessarily true?
No, even for continuous distributions, it could turn out that you should have to split rewards equally between multiple players who fall in the highest band in order to incentivize them. What is the example for? I can't think of a quick example for why this will break.
It might be better to do that rather than just give it to the best.
So depending on the distribution, so it could be that some people, they don't even want to participate because they don't have a very good chance of winning. So by doing this, you're giving more incentive for them to participate.
Do you have an answer?
Yeah, so I have a mathematical answer, but I don't know if that gives the intuition. So let's say, I'll give from auction theory what is going on basically. So if you truthfulness in single parameter settings, okay, the single parameter settings means each agent has only one private parameter, is basically you can give it directly in terms of the allocation function. So if this is V and this is x of V, then the allocation function has to be basically monotone. Okay, and if it results in a monotone allocation function, then it is truthful. But if you basically have a non-monotone allocation function like this, okay, but you can't do a non-monotone allocation function. The goal is to do optimization with respect to the monotonicity condition. Then you basically iron this allocation function, okay, which means you basically flatten it out in this region, which means all values which fall in a particular region are treated equally. Whenever you iron an allocation function, there is going to be discontinuity in how you allocate. Okay, the reason is, so far you are competing only with this set of people with values here. If your value slightly increases, then you're on par with all these people. Okay. So clearly the probability with which you are going to get served will increase. Similarly here, if your value slightly increases, then you suddenly bypass all these people because you only have a lesser competition here. Okay. You are not treated at par with these people, so there's going to be a discontinuity in allocation function whenever you try to flatten the allocation rule. This discontinuity in allocation function will also result in a discontinuity in payments. The question is, how do you ensure that there is discontinuity in payments? The answer is you basically explicitly disincentivize people to bid in certain regions. A discontinuity in payments means that there are some forbidden zones of possible payments. So if I say that all improvements between 10% and 12% will be treated equally for Netflix, nobody will try to give at 11% accuracy. Okay. Everybody will go to 10, which means the region between 10 and 12 is a forbidden region of payment. Nobody will participate, give that number here. So to get what is available here, to mimic that, in this contest setting, we basically put this restriction. So it flows out of this theory, but I am not able to come up with an example where it's more intuitive to do this. This is the theory though. The discontinuity has to be modeled, and I hope you can see that this basically ensures discontinuity. Nobody will give anywhere between 10 and 12. People will always stick to the lower end of an interval. Right? It's a waste of effort. The other work is what I did again in 2010 when I was an intern, and the motivating question for this work is that computing truthful payments is often more difficult than computing the original allocation function itself. Oftentimes truthful payments is only a secondary consideration. The original problem is the problem to be considered, but the secondary thing is basically more difficult than the primary problem itself, and this is a striking observation which Nissan and Ronan make in their seminal paper, where for many problems it seems like computing truthful payments is much harder than computing the original allocation. Can you compute truthful payments as fast as the original allocation? That's the question we ask. Answer is yes, they can be if you are willing to go ahead with the more relaxed notion of truthfulness called truthfulness in expectation, and you can do this both for single parameter domains, which is answered by Babeyev, Kleinberg and Slivkins, and we also do for multi-parameter settings, and this has application to pay-per-click ad auctions where you do not know the parameters in advance. And I'll just mention one other result. This is basically has to do with revenue of maximization in multi-parameter settings. This has been an open question for long in mechanism design. If you just have one parameter, then you know how to optimize revenue, but if you have if agents are interested in multiple items and they have different values for different items, this question has been open for long, and we basically showed that you can get very simple mechanisms which approximate the optimal revenue by just posting prices on items and allowing agents to take their favorite items. And because this has been open for long, there has been several follow-ups after our work, improving our work on several directions. For example, we make some interesting connections to profit inequalities from statistics. There is an open question in our paper which depended on improving profit inequalities, and this basically created renewed interest in profit inequalities, and the state of the art was improved for profit inequalities, and the open question was also answered. Okay, so I'll conclude with future research directions. One thing which is obvious to people if you see what has been going on in the resource allocation settings is that all these problems have incentives or game theoretic assumptions in them, but the game theory has been completely ignored in these problems for the obvious reason that the non-game theoretic problem was already non-trivial. But the picture is fairly complete now for the non-game theoretic setting. So the goal is to bring back game theory to online algorithms, online resource allocation problems. I'll leave with one simple problem, where you could try bringing back game theory in. You have the same display ad setting, M requests and N advertisers. Advertiser wants I wants at most BI impressions. The only difference is that these bids, Wijs, are privately held. And let's assume that the queries are drawn IID from an unknown distribution. If you just look at a purely online setting without any game theory, the algorithms I presented basically solves this problem with arbitrarily close to 1 approximations. If you look at a purely offline setting without any game theory in it, then the VCG mechanism gets a 1 approximation. But if you mix these two, if you mix online and game theoretic constraints, we don't know how this works. Okay, can you get arbitrarily close to 1, or maybe not? Then you have a hardness of being truthful. This is just like many problems where there are two constraints, where one constraint alone can be treated either of them, but if you mix them, you cannot. And this has been the prime agenda in mechanism design, where computational and incentive constraints can be treated individually well, but if they are combined, you don't know how to solve them. There's a tension. Similarly here, instead of computational incentive, you have online and incentive constraints. Is there a separation here? Is there a hardness of being truthful? What can you do even if you know the distribution? That is not known. And there is unknown distributions and separation between IID and random permutation and so on. There's a whole list of questions here. That's it. Yeah. Thanks for listening.
Any more questions?
So, like for the standard, not the IID model, but you can try to do this game synthetic thing for the ghost case.
Yes.
Like which has a 1 minus 1 ODE or something. So, does that carry over?
No, even in the worst case, it's not clear whether you can get that in with game theory, because all the MSCV, as I said, is purely algorithmic.
So I also a naive question. So in the you try to optimize in the sort of stochastic setting expected value of the algorithm over expected sort of optimal value over the distribution. So what if you take expected value of the ratio instead of a ratio of expectations, just sort of in a way it's if, for example, the optimum values of your instances can differ a lot, right? So you are first averaging over all of them and then take expectation. But what if you
That's true. That's a stronger thing. Yeah, that's why one of our results, for example, is a high probability result, which is better than the ratio of expectation. As I said, or this holds with a high probability that you can get this 1 minus square root gamma log n. Yeah, that is a stronger benchmark. And yes, the 1 minus square root gamma I presented depends on we using the ratio of expectations. So I'm not sure. Yeah.
Incomparable. It's not one is stronger than the other.
Yes, but I mean, for at least the kind of instances he said where the opts could widely vary over different things, it could be that is stronger.
Any more questions? This time the speaker.